there, everybody! Welcome to episode number 549 of this here electronic engineering podcast called Amelia's Weekly Fish Fry. Brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. Step right up, ladies and gentlemen, because we're talking about direct RF, the critical needs for military and aerospace, radar, and electronic warfare today, and the world's first liquid hydrogen flight. So first, please welcome Rodger Hosking from Mercury Systems to talk all about direct RF. Hi, Rodger. Thank you so much for joining me.
A pleasure to be here, Amelia.
Excellent. Okay, so Rodger, we're talking about how direct RF can revolutionize military EW and radar systems. But before we dig into the details, what are you seeing as the critical needs for military and aerospace radar and electronic warfare these days?
Well, one of the things is we're getting requirements for wider bandwidth coverage of the signals that radar, EW, SIGINT are required to detect and also to generate signals for. The second thing is we want to be able to cover those signals that can appear across a wide different band of center frequencies from very low to very high. So a span where these bands are located can be extremely wide. And the other thing we need to do is we need to do some extremely fast response time from a signal coming in, making a calculation, and then sending a response back out into the field. This is particularly critical for countermeasures, where the response time is everything, especially if you're a fighter up in an aircraft and you're being chased.
Right. Now, Rodger, what exactly is direct RF and what kind of applications would this be a good fit for?
What it really means is that the A to D converter is digitizing the radio frequency signal directly without having to go first through a down conversion frequency stage, which has traditionally been the only way that we could capture those very high frequency signals. They would have to be processed in an analog down converter. With these new direct RF A to D converters, they're fast enough now so that those converters can directly digitize the high frequency RF signals that previously had to be down converted. So the term direct RF is evolving with the technology of the data converters that are used to capture the signals. 10 years ago, direct RF might be a 2 gigahertz signal, but now it's a 20 gigahertz signal.
So, what kind of benefits are we looking at with direct RF?
What we're doing is by eliminating all of the analog RF down conversion and the up conversion circuitry that you need if you need to transmit, you are shrinking the size, weight, and power of radio systems and really changing the architecture of those software radio systems to be simply some filtering and amplification before the data converter instead of having all of that other circuitry. So now these systems can be put into smaller footprint platforms. You can do all of the circuitry up near the antenna because it's small enough to fit near the antenna instead of having to pipe down analog RF signals in coaxial cables and then do all the processing down, say, below decks if it's on a ship.
So, direct RF does have some trade-offs as well, right?
One of the trade-offs is if you have a strong interfering signal, you will then compromise the dynamic range of the small signals that might be very nearby, because if you set the gain to accommodate the large signal, the weak signals are going to have very little gain. So what you can do is you can apply adaptive filtering, analog filtering, before the signal gets to the A to D converter to notch out a strong interferer. And Mercury does have monolithic, tunable RF filters that can do that job.
Excellent. Now, speaking of Mercury, what are you guys doing in this realm?
Well, what we're doing is we're developing a couple of different technologies. One is the new RF SIP packaging technology, which takes very high speed data converter chiplets and it combines them in the same package with a high performance FPGA using a direct interconnect from the chiplet A to D converter, D to A converters to the fabric. So you have a very wide parallel fast bus that doesn't that removes the bottleneck that you'd otherwise have to have if you had an external discrete data converter. We're doing that. Other people are doing that. It's the way of the future.
All right. So, Rodger, I know you've been rather involved with this integration with Mercury in the last many months. So, how's it going?
It's going really well. We're doing some difficult things because the way we have done things for 35 years is now changing to the way that Mercury does things. And so our systems need to adapt, and we've been doing that. Fortunately, we have some really smart, talented, and helpful people at Mercury who want us to succeed and have done a lot to support that effort. There's still a lot of details to work out, as there always will be with any integration. But when you have people helping you do it, it makes it a lot easier.
Absolutely. Well, Rodger, I think that's all I have time for today. Thank you so much for joining me.
Amelia, it's always a pleasure. Thank you.
Did you hear about the new aircraft that runs on liquid hydrogen? Well, if not, let me introduce you to H2 Fly's new twin fuselage aircraft called the Pipistrel Taurus G4. Now, not only is this new aircraft super cool, the world's first piloted liquid hydrogen flight, but it could also be a solution to decarbonizing long range flight. So, why haven't there been liquid hydrogen flights until now? Yeah, I hear you loud and clear, my clever engineering audience. Because it's a nightmare to work with. Yes, in order to maintain liquid form, you need to keep it to around an absolute zero temperature. It boils at just 20 Kelvin given ambient pressure levels. On the other hand, it does emit nothing but water when it's burned, carries about 2.8 times as much energy as jet fuel by weight, which can mean a lot in aviation, and can be run through a fuel cell to generate power for electric motors. But even though it can hold a high energy content by weight, volumetrically its energy density is actually really low. Basically, you need a tank almost 4 times larger than your regular jet fuel tank to carry the same amount of energy. So, yeah, less weight, but heavier equipment. Keeping all of that in mind, H2 Fly says that they have been able to double the range of this aircraft by switching from gaseous hydrogen fuel to liquid, taking it from 466 miles to 932 miles. So this aircraft is a little oddly shaped. So the pilot actually sits in the fuselage on the right, and the fuel system is isolated from them, rightly so, on the left-hand fuselage. The hydrogen converting fuel cells and electric propulsion system are all housed in the middle section of the aircraft. So, we're talking about the world's first piloted liquid hydrogen flight, right? Actually, no. H2 Fly says they have completed not one, but 4 total missions out of their airfield in Slovenia. They say that this aircraft saw safe and efficient operation through multiple test flights, and that these test flights did reflect their expected range figures. H2 Fly's co-founder, Professor Joseph Kallo, says this about these first test flights. He says, this achievement marks a watershed moment in the use of hydrogen to power aircraft. Together with our partners, we have demonstrated the viability of liquid hydrogen to support medium and long-range emissions-free flight. We are now looking ahead to scaling up our technology for regional aircraft and other applications, beginning the critical mission of decarbonizing commercial aviation. Wow. All right, so let's talk about that scaling up part. Right now, H2Fly's technology is working fine with small, lightweight, low-altitude test aircraft. But they want to move into freight and commercial passenger markets. Of course they do. So, they are now working on a next-generation modular fuel cell unit that can stack up to satisfy megawatt-scale power demands and operate at altitudes as high as 27,000 feet. So, think of a regional airline with like 20 to 80 seats. That's probably the next realistic step. But speaking of realism, we're probably looking at least the 2030s until H2Fly gets a liquid hydrogen flight into commercial airspace. Right now, they aren't making any promises for timelines, which is smart, considering how long it's going to take for development, testing, integration into actual airframes, and certification. It's going to take a while, but for the future of aircraft, this is huge. And I am excited to see their progress in the years to come. So, if you want even more information about Mercury systems, direct RF, or H2Fly's new liquid hydrogen-powered electric aircraft, I've included a couple links below the player on this week's Fish Frying page on eejournal.com and in the YouTube description for this week's episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If you're into Twitter, you can monitor our tweets at EEJournalTFM. And don't forget, if you would like to follow my personal Twitter account, check out Amelia D 1978. And hey, if LinkedIn is more your thing, sure, I dig it. You can follow us or me on LinkedIn as well. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And you can subscribe to our EE Journal YouTube channel as well. Also, by clicking the links below the player on this week's Fish Frying page, you can subscribe to this here podcast through Spotify, Podbean, or Apple Podcasts. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of September 15th, 2023, I'm Amelia Dalton, and you've been fried.